Okay, welcome to Robotics 1. Today's lesson is very important, so I just need to write it down. Important lesson. Because your next quiz will utilize the material from today's lesson. So let's quickly recap what we have been doing so far. We are trying to study the dynamics of robots. Now, the way we started with a simple pendulum. Now, this simple pendulum has mass m and length L. So this rod was assumed to be massless, and the entire mass was concentrated at the end. So for that, when we looked at the mass moment of inertia, we looked at mass moment of inertia. The equation that I gave you was mass multiplied by radius of gyration square. Gyrations means revolving or moving. So if you look at the radius of gyration for this particular problem, it is L. So the value of I is going to be mL square. But this is a very simple approximation. In actual practice, you will never have a rod that is massless. So this is called as simple pendulum. Simple pendulum. And the actual pendulum is something like you have a mass that is distributed across. So you have a pendulum and the mass is distributed. So mass is distributed. So the total mass is m, but this total mass is made up with these teeny tiny particles that are dispersed in this mass. Now, we studied the concept of centroid and center of gravity. So what we can say is this mass is concentrated at this location CG. So the total mass, mass is equal to m, and we assume that total mass to be concentrated at CG. And what I'm going to do is I'm going to say the distance from CG. You perform the calculations for CG, you use the concepts that you studied in statics and dynamics, and you found out the CG is at radius r. And now, if we want to formulate the differential equation of motion when the mass is distributed. So please understand, in this particular case, the mass is distributed. It's not concentrated at the end. So I'm going to use the Lagrangian approach. And what we do in the Lagrangian approach is first we want to find out the kinetic energy, and then we have to find out the potential energy. Now what I want to give you here is a generalized expression for kinetic energy. The expression for kinetic energy is mass multiplied by velocity at the CG square multiplied by 1/2. So 1/2 mass multiplied by velocity of velocity at CG plus 1/2 I, which is mass moment of inertia at CG multiplied by angular velocity square. So I need to write these down. So V is the velocity at CG and omega is the angular velocity. Now please note, angular velocity basically is nothing but this. I'm going to call this omega. Angular velocity, whether you consider it at CG or you consider at any other location, it's going to be the same. So this is very important. Omega at CG is equal to omega at any other location. So omega at CG is equal to omega at any other location. So value of omega does not change. But the linear velocity, and this is very important, this is linear velocity, changes depending upon where you take it. So what we want to do is we want to find out the velocity at CG, and we have to find out mass moment of inertia at CG. And this is super important. This is mass moment of inertia at CG. Now, this mass does not matter. This is the total mass. And this important expression will be used whenever we try to derive the dynamical equations of motion or equation of dynamics for robot arms. Then we have something called as the potential energy, which is V, which is potential energy. And whenever we find out the potential energy, we are going to find out the potential energy with respect to the center of gravity. So for an example, in this case, potential energy is going to be R cosine of theta, assuming this angle is theta. If this angle is theta, R cosine theta times M times G. It's not going to be the total length. And I need to specify that. Say the total length of this irregular object may be L. But this L does not come in the picture whenever we try to derive the kinetic energy or the potential energy. This is super important. Now, why is this important? Because when we are trying to study the actual robot, the robots are going to have some complicated shapes, very complex shapes. So how do you find out the mass moment of inertias for these complicated shapes? And that case, SolidWorks or CAD softwares come to rescue. So whenever you import that geometry inside the CAD software, you can right click and it will give you something called as the principal moments of inertia. And those are the moments of inertia that we will use. And we will look at that when we study an actual problem. But let's try to solve few simple problems with this concept. So what I'm going to do is, first and foremost, I'm going to give you an expression for the mass moment of inertia for a rectangular rod. So consider a rectangular rod. And for this particular problem, I'm going to assume a three-dimensional shape. I'm going to assume a three-dimensional shape, and then we will try to simplify our assumptions in subsequent problems. So I'm going to call this length as L. And I'm going to call this length, this dimension as height h, and I'm gonna call this dimension as width. First and foremost, let's identify the CG. So CG will be somewhere at the center. So CG is going to be somewhere over here. Let's identify the axes. So the rod, the rectangular rod, is gonna have axes like this. So you have an x-axis, you have a y-axis, and you have a z-axis. And now what it means that this rectangular rod, if assuming the mass of the rod is m is the mass of the rod, and this is the total mass which is distributed everywhere. So if you were to add all the masses, the particles, then the total mass is m. And we have found out the CG, and this CG is going to be half of length, half of width, and half of height. So if you really want to look at where this CG is located, if you look at the side view, the CG would be at this location. And that means this distance is going to be W by 2. If you look at this distance is going to be H by 2. And if you look at the top view, if you look at the top view, and the CG would be at the location L by 2. So this is where the CG is going to be. So this is center of gravity. This is center of gravity. Now I want you to assume the rotations about Z. So assume that this rod could rotate around Z. This rod could potentially rotate about Y, and this rod could potentially rotate about X. So let's try to understand the concept of kinetic energy. I'm gonna say omega Z is the rotation about Z. So imagine for some reason you have a hinge and this rod starts rotating about Z. You have omega X, which is the rotation about X. And you have omega Y, which is the rotation about Y. And what I want to do is, I want to find out first total rotational kinetic energy. So what I'm going to do is, I want to find out total rotational kinetic energy. And the expression for total rotational kinetic energy is very simple, which is, I'm going to write this down, 1/2 IZZ, mass moment of inertia about ZZ, multiplied by omega Z square, plus 1/2 IXX multiplied by angular velocity square about X, plus 1/2 IYY omega Y square. Now the question is, what is IXX, what is IYY, and what is IZZ? And I'm gonna give you expressions, so please pay attention. And there's a symmetry that you can follow. Look at IZZ. What are the two important dimensions here? You have this dimension and this dimension. So IZZ is perpendicular to the plane XY. So basically, z-axis is perpendicular to the plane that comprises of x and y. So the equation is 1 by 12 m. Now, these two dimensions are, one is L square plus H square. So IZZ, this dimension is perpendicular to the plane XY. So L is the dimension around about X and H is the dimension about Y. Now let's look at IXX. So for IXX, the the it's the two dimensions that are interested in, the perpendicular dimensions are H and W. So IXX is 1 by 12 m. You have H square plus W square. And last but not least, I want to show you the dimension around Y. So the dimension around Y, which is IYY, you have L and you have W. So 1 by 12 m L square plus W square. That is how you would find out the moment of inertias about the CG of a rectangular rod. And rectangular rod is the simplest approximation for the robot arm. Rectangular rod is the simplest approximation for the rectangular rod. And just for the completion, let me just write this down. So these are the dimensions. Now let's take a very simple approximation of the rod. It is called as the slender rod. So one level approximation is called as the slender rod. So in slender rod, the most important dimension is the length of the rod. So the most important dimension is the length of the rod. And we assume the other two dimensions, which is width and height, they are approximately 0. So if you have a slender rod, and let's try to draw this slender rod in 3 dimensions just for completion purposes. And now let me identify the coordinate system. So this is the coordinate system. This is X, this is Y, and this is Z. So if you want to find out IXX, IYY, and IZZ, you will use the exact same expressions that we derived for the rectangular rod, except you will substitute W is equal to 0 and H is equal to 0 in that expression. So what I'm going to do is, I'm going to write these expressions down. IYY is 1 by 12 m L square. IXX is equal to 0 because W and H, both of them are 0. And IZZ is equal to 1 by 12 m L square. So this is what we mean by a slender rod. However, the practical robots, they are going to be not as simple as the rectangular rod or a slender rod. For an example, you could have a practical robot that link shape is maybe super complex. So something like this, you have a practical robot where the shape of the robot is something like this. And then there is a hole here, there is a slot here, and then there is another hole here, there is another hole here. So what would you do in that case? In that case, we will actually do a CAD model. So you will actually do a CAD model, and once this geometry is inside the CAD model, the centroid will be calculated numerically by the CAD model. And then you can right click and you ask for principal moment of inertia. And these principal moment of inertias would be written in a slightly interesting fashion. It will be a 3 by 3 matrix. And then it will be Ixx, Iyy, Izz, and there will be zeros on the off diagonal terms. So when you import a complex geometry inside the CAD model and you ask the CAD model to compute principal moment of inertia, it will give you a matrix. This is called as inertia tensor. And depending upon at what location this is calculated, the values would be different. But you should always find out at CG. That is absolutely important. At least for the robotics one, where we are studying the Lagrangian equations. So when you are trying to study dynamics of a practical robot, you construct the geometry inside the CAD software and then click, and then what it will do is it will numerically calculate these principal moments of inertia. Now what I'm going to do is I'm going to look at a very simple dynamics problem with a slender rod. Now we looked at the simple pendulum as our starting example. Now let's look at something called as a compound pendulum, or let's consider a slender rod. So now what I have is, instead of a pendulum where I had mass at one end and the rod was massless, now I have this distributed mass M. Distributed mass M. And I'm gonna give the length of this rod as L. And let's try to derive the equations of motion. So first and foremost, where would be the centroid in the case of a slender rod? The centroid is obviously going to be at this distance, which is L by 2. This distance is L by 2. And let's try to write the expression for kinetic energy. Kinetic energy for this rod is mass, 1/2 mass, linear velocity at CG square plus 1/2 I at CG multiplied by omega square. Now, if you were to look at the axes, you will realize I can set up the axes like this. This is my x-axis, this is my y-axis, and z-axis is coming out. So to be very precise, this is actually my IZZ. So what I'm gonna do is I'm gonna go and write this expression down, which is 1/2 m. Velocity is always omega times r, where omega is the angular velocity and r is the radius. So the radius in this case is L by 2, and omega is nothing but theta dot. So theta dot is the angular velocity let me give you value of theta. This is theta. So theta dot is the angular velocity, and L by 2 is nothing but the radius. So this velocity is going to be something like, okay, if I were to show velocity in the same direction, so this is going to be V, which is L by 2 theta dot. Now the angular velocity, so it's going to be theta dot times L by 2 square plus 1 half. For the slender rod, the mass moment of inertia about ZZ is m L square by 12. So m L square by 12. And omega is theta dot square. So when I write this equation down, this equation becomes 1 half m L square by 2 square theta dot square plus 1 half m L square by 12 theta dot square. So this expression can now be written as 1 half m L square by 2 square is 4 plus m L square by 12 theta dot square. So this expression can now be written as 1 half m L square by 3 theta dot square. So that is what the equation simplifies to. So when you combine the terms, now let's write the equation for the potential energy. Potential energy, here we will have to be very specific. Potential energy is always with respect to Cg, where the mass is located. Even though the length of this slender rod is L, mass is located at distance L by 2. And considering this as datum, the vertical distance, this vertical distance is L by 2 cosine of theta. So this distance is L by 2 cosine of theta. And since it's going below datum, the potential energy is minus m times g L by 2 cosine of theta. And please recognize that there is a negative sign because the CG is below datum. We are going down. Now we have to formulate the Lagrangian. So let's start. I'm going to formulate the Lagrangian L is equal to T minus V, and T is 1 half m L square by 3 theta dot square minus V. Let's not forget there is another minus sign, mgl by 2 cosine of theta. Now we got the Lagrangian. Now what we need to do is we will solve this Lagrangian using the Lagrangian equation. Let me just write this Lagrangian, m L square by 3 theta dot square plus mg L by 2 cosine theta, and the expression for Lagrangian is d by dt partial L by partial theta dot minus partial L by partial theta. So let's go step by step. D by dt partial L by partial theta dot, which means all other terms except theta dot is constant. So this is going to be 1 half ml square by 3 multiplied by 2 theta dot plus 0 minus, here it's partial L by partial theta, which means theta dot is going to be 0. So first term is going to be 0 plus mgl by 2, derivative of cosine theta is minus sine theta. So this is going to be minus mg L by 2 sine of theta. So when I solve this, I need to take the derivative, and this is the full derivative. This is not the partial derivative. So when I do the full derivative, 1/2 gets cancelled, and I get ml square theta double dot, because it's a full derivative, plus mg L by 2 sine theta is equal to 0. And this is the differential equation of motion of the slender rod. This is the equation of motion for slender rod. And this equation can be solved numerically, and we will be able to get the solution of the differential equation. Any questions up to this point? Now, if you want to use MATLAB to do the whole calculation, please note the only input that MATLAB would need at this point is this. So this would be the input to MATLAB, and MATLAB would derive the equations. Now let's try to understand this problem in a slightly different context. Now, if you look at the way the problem was set up, this is a planar problem. So this is planar, which means this slender rod was only oscillating around z. So planar means no motion about x or y. However, if you look at practical robots problem, the robot problems are actually 3-dimensional. So which means you would have a slender rod or a link that will have motion in 3 dimensions. So how do we solve a problem when the motion is in 3 dimensions? So let me set up the problem. So consider a rod and now this rod is capable of moving or rotating in x, y, and z direction. So this is x, this is y, and this is z. And for the most general case, let me say I have Ixx, which is the mass moment of inertia about x-axis. I have y, which is the mass moment of inertia about y-axis, and I have Izz. And these are given to us or computed by a CAD software, or they are, for the sake of discussion, they are known. And the units are kilogram meter square. So Ixx, Iyy, and Izz is given to us. Now let's assume, for the sake of discussion, that there is a spherical joint here. So what I have here is a spherical joint. So this is a spherical joint. So spherical joint or a ball or socket joint, what it means is this guy, this link can move around X, around Y, around Z. So you could have a translation about Z, you could have translation about X, you could have translation about Y. Now, some of you may ask me, well, what does it mean when you have translation about X, translation about Y, and translation about Z? What it means, what I'm trying to say here is, it could have VZ, it could have Vx, and it could have Vy. I mean, it may not be physically realizable in this particular configuration, but I want you to understand that because of the nature of the spherical joint, you could have a component of velocity, component of linear velocity about z, a component of linear velocity about x, and you could have component of linear velocity about y. Now, if I were to ask you, find out the kinetic energy, the expression for kinetic energy is kinetic energy in translation plus kinetic energy in rotation. Now, how do we find out the kinetic energy in translation? Again, first find out what is the total mass, and we assume this total mass m is located at Cg. Kinetic energy in translation is nothing but 1/2 m Vx square plus 1/2 m Vy square plus 1/2 m Vz square, where Vx is the component of velocity about in x direction, component of velocity in y direction is Vy, component of velocity in z direction is Vz. So this is the kinetic energy in translation, plus the kinetic energy in rotation is 1/2 Ixx omega x square plus 1/2 Iyy omega y square plus 1/2 Izz omega z square. So now you have the expression that is needed for kinetic energy. And please note, this is a three-dimensional equation. So you are going to have Vx, Vy, Vz. They represent the translational motion about x, y, and z. And you have omega x, omega y, and omega z. That is nothing but the rotational motion about x, y, and z. Now let's try to find out the potential energy. Now in this particular case, how do you find out the potential energy? One thing I want you to understand, potential energy is always about gravity. So find out in which direction the gravity is. So for an example, this is the direction in which the gravity is acting. If this is the direction in which gravity is asking, what you need to do is you need to find out the component which is uh, about gravity. So this length, and I'm going to show it over here, this is the length, and depending upon how this rod is oriented in 3 dimension, this length would be changing. So for an example, if the rod has two angles, theta and psi, then you will have to take appropriate components, and I'm going to call this as uh, let me show it with like L. This is L, and the potential energy is minus mgl. So whenever you find out the potential energy, you will have to take the component around about in the gravitational direction. Now I will answer the questions about the homework at the end. Let me finish the discussion on what we are supposed to cover today. Now, how do you find out the kinetic energy and potential energy when you have a robotics problem? The good news is, believe it or not, the problem is actually solved. Whenever we are working out the forward kinematics, the problem is actually solved for us. And what I'm going to do is, I'm going to set up the problem. I will try to find out the kinetic energy and potential energy for one or two problems. And in next class, we will see how we can solve this problem using MATLAB. And the next slightly different iteration there is, what would we do in the case of practical robots if the shapes of the links are not like circular or rod, they are some non-standard shapes? How do we address that issue? And that will come in future classes. But let me work out a problem that we are familiar with. Now this problem, it's similar to your homework problem, which I worked out in last class. And this is problem we solved in lecture 12. And we actually used MATLAB to work out and find the dynamical equations of motion, and then we analyzed using MATLAB. In this problem, what we have is we have a revolute joint, then there is a link. Now what I'm going to do is, I'm going to make this link, unlike the previous problem, I'm going to make this link a solid link. So what we have is, we have a solid link, and then we have a revolute joint. On this solid link, what I have is, I have another revolute joint. I have another revolute joint, and this another revolute joint is attached to another solid link. So what I have is, I have another solid link, and just to make it proportionate, let me draw the revolute joint like this. So I have link 1 and I have link 2. In this case, the difference being, these links are not massless, but the mass is distributed. So this link has mass m1, which is distributed, and this link has mass m2, that is again distributed. Now, how is this problem different than the problem that we solved in last class? In last class, we had a revolute joint, but the total mass for the link 1 was concentrated at the end. Then we had another revolute joint. And the mass for link 2 was concentrated at the end. So you had M1 and you had M2. Unlike that problem, now the mass is distributed. Okay, now we have the first revolute joint, which is R. We have a second revolute joint, and this is the end effector. This is the coordinate of the end effector. This is where the end effector is. Now, the way we would solve this problem, it's first and foremost, we will set up the coordinate system. And we know how the coordinate system is going to look like. So I will quickly draw the coordinate system: x naught, y naught, c naught, and then you have another coordinate system. You have y1, z1, and x1, and you have one more coordinate system at the end, which is x2, z2, y2, x2, y2, z2. I'm not going to derive the equation for forward kinematics, but we will refer to the equations that we derived in lecture 12, and I will refer the notes. So if you just want to uh, refresh yourself, you can go to Canvas and quickly download the notes for lecture 12. Now, what I'm going to do is I'm going to find out the centroid of link 1. The centroid of link 1 is over here. So this is where mass M1 is concentrated. Centroid of link 2 is somewhere over here. This is where mass M2 is concentrated. Now my first and foremost objective is to find out the equations for kinetic energy. And when you have a distributed mass, and when you have a robot which has something, the links, something like this, it's not a trivial task. And we have to proceed very systematically. And the reason I say we have to proceed very systematically is because you will be having velocities in 3 different dimensions, x, y, and z, and you will have angular velocities in 3 different dimensions, and you have to find out the kinetic energy for link 1. So I need to write this down. We have to find out kinetic energy for link 1. Then we have to find out kinetic energy for link 2. Then we have to find out kinetic energy for link 2. This will be the total kinetic energy. But please understand, when we find the kinetic energy for link 1, you are going to have kinetic energy of translation. You will have kinetic energy of rotation. Kinetic energy for link 2 will be kinetic energy of translation. Then you will have kinetic energy of rotation. Then you will have to find out the potential energy. When you find the potential energy, same thing, you will have to find out the potential energy for link 1. And then you will have to find out the potential energy for link 2. The good news is we already have the information that we need. So what are we going to look from the forward kinematics? Look at the solution for the forward kinematics. Forward kinematics. And let's try to see what information we need. For kinetic energy in translation, let's look at link 1. I'm going to look at link 1. Now I'm going to look at link 1 and I'm going to look at kinetic energy in translation. To find kinetic energy in translation, I need the velocity of mass m1. How do we find out the velocity of mass m1? What I need to do is, I want you to look at your homogeneous transformation matrix 0h1. I want you to look at the homogeneous transformation matrix 0h1. In this homogeneous transformation matrix H01, you are going to have a 3 by 3 matrix here that represents the rotation 0r1. You are going to have 0, 0, 0. You are going to have 1 over here, and you would have px, py, pz. Now px, py, pz is the distance between frame 1 and frame 0. I want you to look at expression for px, py, and pz. You would realize the expression, and at this point what I'm asking you to do is I want you to look at 0h1 from lecture 12. You will notice your px is 0, py is 0, and pz is equal to a1. Are you with me so far? If you look at your 0h1, you're gonna have px is equal to 0, py is equal to 0, and pz is equal to a1. What that means is this is a1. Now what I want you to do is, with this information, I want you to tell me the coordinates. I want you to tell me the location of mass m1. And location of mass m1, and I'm going to write this down here. Location of m1 is 0 about x naught, 0 about y naught, and a1 by 2 about z naught. Are you with me so far? So this mass m1 is located at 0, 0, a1 by 2 from uh, the reference frame, which is the inertial frame, which is the 0th frame, which is over here. Any questions here? So I'm interested in finding out, I know the location. I'm interested in finding out the velocity Vx. So for mass, I want to find out Vx of m1, Vy of m1, and Vz of m1. I'm interested in finding out the velocity in x direction, velocity in y direction, velocity in z direction for mass m1. So what I do is I take these expressions for location, and in this particular problem, the good news is the position of mass m1 about x naught is 0, position of mass m1 about y naught is 0, position of mass m1 about z naught is again a1 by 2. But please understand, a1 by 2 is a constant. So this guy is a constant. So what it means is when I take the derivative, velocity x of mass m1 is 0, velocity y of m1 is 0. Since a1 is a constant, derivative of constant is 0. So I have all these three velocities at 0. And now let's try to look at this little bit intuitively. So this link does not have any translation in x direction, y direction, or z direction. That's why we don't have any velocity in x direction, y direction, and z direction. Once again, this mass m1 does not translate about x naught, y naught, or z naught. It stays where it is all the time. That's why the velocities are 0, which means for link 1, the kinetic energy of translation is 0. And why is it 0? Because the velocities are 0. Now, what I want to do is, I want to go a step further. We will continue our analysis on link 1. We are still on link 1. I want to find out the kinetic energy of rotation. Kinetic energy of rotation. Kinetic energy of rotation for link 1 is given as 1/2 Ixx omega x square plus 1/2 Iyy omega y square plus 1/2 Izz omega z square. Now the question is, where do we get omega x, omega y, and omega z? If you recollect, we have derived the equation for Jacobian. So remember, we derived Jacobian equation. And the Jacobian equation was written as omega x, omega y, omega z. I'm going to duplicate that relationship here. 0 r 0, 0, 0, theta 1 dot plus 0 r1, 0, 0, theta 2 dot. And we derived this notes lecture 12. Now this is the overall Jacobian. Now what I mean by overall Jacobian is this is for link 1 and the whole thing is for link 2. We did that for the end effector. Since end effector is part of link 2, this whole expression is for link 2. So now what I want you to do is, for a minute, I want you to look at part of the Jacobian equation. And I'm going to show you which part of the Jacobian equation I want you to look at. Since we are looking at link 1, I want you to just focus on the expression for the link 1. So since we are looking for link 1, I will write this expression omega x, omega y, omega z for link 1 is equal to 0 r 0, 0, 0, theta 1 dot. And 0 r 0 is nothing but an identity matrix 1 0 0 0 1 0 001 multiplied by 00 theta 1 dot, and when you perform this calculation, this will give you the answer to this is omega x for link 1 is equal to 0, omega y for link 1 is equal to 0, and omega z for link 1 is equal to theta 1 dot. Now let's see if it kind of uh, makes sense. So what we are trying to see here is, if you look at the rotation of this link is about this axis. So this is theta 1 dot. Let me use a different color. So theta 1 dot, this is theta 1 dot. So this link is going to rotate about z naught axis. The link does not have any rotation about x naught. This link does not have rotation about y naught. So since there is no rotation about x naught, there is no rotation about y naught, it will not have angular velocity about x naught, angular velocity about y naught. It will only have angular velocity about z naught. So this is 0 plus this guy is 0. The only kinetic energy this link will have is omega izz theta 1 dot square. This is the kinetic energy for link 1. So with this information, I am able to find out the total kinetic energy. So kinetic energy total, and we are still on link 1. For link 1, the total kinetic energy for link 1 is from this previous expression that we found out over here. The linear kinetic energy is 0 and the rotational kinetic energy is 1/2 Izz theta 1 dot square. Are you with me so far? Now let's move on to the kinetic energy for link 2. So we have to find out, same approach, we have to find out kinetic energy for link 2. Now what I want you to do is, how would we get the information for kinetic energy for link 2? We will adopt the same approach. Somehow from matrix 0H2, I want you to look at the matrix that you have 0H2. 0H2 matrix will have a rotational matrix. This is 0R2. It will have 0, 0, 0. It will have 1. And I'm going to write this expression here. And then I'm going to discuss this in just a second. The expression that you are looking at is A cosine theta 2 cosine theta 1, A2 cosine theta 2 sine theta 1, and A1 plus A2 sine theta 2. Note, these expressions are for the end effector. This is the position so end effector position. No, in today you won't need the information from this lesson, because for the homework the mass is not distributed, mass is fixed at one end, so you don't need the information from this lesson. So now here is the tricky part. This is the position of the end effector, and I need to write this down. So if I ask you, where is end effector located? So the question is, where is end effector with respect to frame 0, with respect to origin? You will tell me the coordinates of the end effector. The coordinates of end effector are, I'm going to call this px, py, and pz. So coordinates of the end effector are px, py, and pz. But the question I want to ask here is, where is mass m2 with respect to origin? Clearly, mass m2 is not located where the end effector is. Mass m2 is over here. Mass m2 is over here. And just for the sake of discussion, this distance is a2. This distance is a2. So if you think about it, if a2 is the total length, the mass is actually located at distance a2 by 2. So the mass is at half link length. So it's at half link length, which means it is at distance a2 by 2, or in our case, which is L2 by 2. So with the information that I have over here, I can simply say the coordinates of mass m2, or the position of mass m2 px. This is for mass m2. This is not end effector. It is a distance L2 by 2 cosine theta 2 cosine theta 1 py m2 is at distance L2 by 2 cosine theta 2 sine theta 1 pz m2. Now this is where the tricky part is. So mass m2 is at the distance, the z distance is a1 plus a2 cosine of theta. So the distance that's gonna be is equal to a1 plus L2 by 2 sine theta 2. So please note, a1 here and a1 here will remain same, because when you look at the z component, you are gonna have for a1 plus L by 2 sine theta 2. Okay, so the good news is we found out the positions of mass m2, but we actually need velocity of mass m2 in x direction. We need velocity of mass m2 in y direction, and we need velocity of mass m2 in z direction. So I need these velocities. How do I get these velocities? And these velocities can be obtained from the Jacobian expressions that we derive. And what I'm going to do is, I'm going to write down those expressions, and you have these expressions written. I actually manually derived these expressions. So I will write these expressions down. L2 by 2 minus sine theta 2 dot cosine theta 1 minus L2 by 2 sine theta 1 dot cosine theta 2 L2 by 2 minus sine theta 2 dot sine theta 1 plus A2 cosine theta 1 dot cosine theta 2, and here you will have 0 plus L2 by 2 cosine theta 2 dot. So these are the velocities. These are the velocities of mass M2. Now, with this information, I'm able to find out the kinetic energy of mass M2 in translation. So, kinetic energy of mass M2 in translation is equal to, and I'm not gonna rewrite those expressions. M2 Vx2 square. This is the velocity x of M2 plus 1/2 M2 Vy2 square, which is velocity y of mass M2 plus 1/2 M2 Vz2 square, which is the velocity in z direction of mass M2. What was Vz2? Vz2 is this. In Py, okay, let me see. Py sine, yeah, Py sine theta 1. Theta 1. Cosine theta 2 sine theta 1. Cosine theta 1. Yeah. Yeah, sine theta 1. So Vz2, now story does not end there. We need to still find out the kinetic energy in rotation. Kinetic energy in rotation comes from the equation of Jacobian. And for this, what you will do is you will use the entire Jacobian expression. In other words, you will have omega x, omega y, omega z, which is equal to 0 r 0, 0 0 theta 1 dot plus 0 r1, 0 0 theta 2 dot. You will use this entire expression, that will be omega of mass or omega of link 2, and that expression we already derived, and I will give you omega x is equal to sine theta 1 theta 2 dot, omega y is minus cosine theta 1 theta 2 dot, and omega z is theta 1 dot. This is for link 2. So the kinetic energy in rotation for link 2 is 1/2 Ixx omega x. I'm going to call this omega x2, omega y2, omega z2, omega x2 square. So this guy plus 1/2 Iyy omega y2 square, which is this guy, plus 1/2 IZZ omega Z2 square, which is nothing but this guy. Now the total kinetic energy. So the total kinetic energy is nothing but for kinetic energy translation for mass 2 plus kinetic energy of rotation for link 2. And that gives you the total kinetic energy. So total kinetic energy. Total kinetic energy is kinetic energy for 1 plus kinetic energy for 2. So you are gonna get a very long expression for total kinetic energy. But we will typically try to use MATLAB to solve this problem. Next part is easy. Now we want to find out the potential energy. And I'll need 2 minutes to discuss potential energy. So there will be potential energy for mass M1 and mass M2. Now, how would you get the potential energies from mass M1 and M2? Please note, you already have the locations of masses. So I'm going to go back, and please note, you have Pz of mass M1. So the potential energy for mass M1 is nothing but mg Pz for M1 plus mg Pz for M2. Now you will see where would Pz for M1 will come from. Pz from M1 will come from here. So this is Pz for M1. This is Pz for M1. And where would Pz for M2 will come from? Pz for M2 will come from here. This is the Pz for M2. So you already have the expressions for Pz for M1 and Pz for M2. And once you have this, you can formulate your Lagrangian kinetic energy minus potential energy and send that to MATLAB, and MATLAB will give you the solution. All right, with this, I'm going to stop here.